Hi everyone, welcome to the practical part of the course where you'll learn how to perform speech-to-text transcription with Python. Let's start by setting up the environment for our task. We'll use the Anaconda distribution to run the necessary Python code, specifically the Jupyter Notebook platform. If you don't have these installed, proceed with the lesson to learn how to set them up. If you have Anaconda and Jupyter on your system, you can skip the installation steps and use your existing setup. Please note that we recommend using Python version 3.9, which has proven to work smoothly with the required packages. Later versions of Python include NumPy 2.0, which can cause incompatibilities with other libraries. Therefore, if you have a different version of Python installed, we suggest creating a separate environment with Python 3.9 specifically for this course. The steps for setting this up are covered in the following lessons. Okay, let's first install Anaconda. Open your browser and go to the Anaconda distribution main page. Feel free to skip the registration because it's not an obligatory step to complete the installation. Click Download to get the most recent version relevant to your operating system and wait for the process to complete. After downloading Anaconda, double-click the .exe file to install it. In the window that appears, I'll select Register Anaconda 3 as my default Python 3.12 version, along with Create Shortcuts and Clear the package cache upon completion. Please don't get confused because we're selecting Python 3.12, even though I mentioned we'll use 3.9. Here, we're choosing the latest version available in general. Later, we'll specify which version to use specifically for this project. Okay, press Install and wait for the installation to complete. Good job. You can now start the application to view its main window and explore its features. In the next lesson, we'll demonstrate how to create a new Anaconda environment and set a kernel in Jupyter Notebook. See you then. Welcome back. Before installing the Python packages for speech recognition, we'll create a new environment for our exercise. When you create a new environment in Anaconda, you make a separate space to install specific packages and Python versions without affecting other environments. This approach ensures no conflicts between libraries. You can install the package as you prefer, but the method we show here is secure and widely trusted. However, feel free to arrange your setup as you like, as long as the libraries are installed and the code runs successfully. All right, let's create a new environment in Anaconda. To do this, open Anaconda Navigator and go to the Environment section. From there, choose Create and type an appropriate name. I'll call the environment SpeechEnv. And go for Python version 3.9 because this version proved to work well with the required libraries for speech recognition. Great. Now open Anaconda Prompt or Terminal if you're on Mac to install the required packages. To activate your new environment, type conda activate SpeechEnv, then press Enter. You can see how the text in the parentheses switched to our new environment. Excellent. The next step is to install IPyKernel to organize Jupyter kernels, the computational engines executing the code contained in a Jupyter Notebook. Simply type pip install IPyKernel. Press Enter and wait for the installation to finish. After installing IPyKernel, you can add a new kernel to Jupyter Notebook. To do this, type the following line: Python flag-m IPyKernel. Install --user --name SpeechEnv --display -name, followed by Python and speech environment in the parentheses. This command will create a new kernel and name it with a suitable name for our exercise. You can now go to Anaconda Navigator and install Jupyter Notebook in your new environment. Just click on the relevant button. Excellent. Keep the Anaconda prompt open for now. We'll install the packages necessary for speech recognition in the next lesson. See you there. Hi again. It's time to dive into the speech recognition magic. Let's start gathering our specific packages for audio processing. Begin with Librosa, a Python library designed for music and audio analysis. Librosa lets you load audio files, extract features, and perform various transformations and visualizations. Open Anaconda prompt or terminal if you're using Mac, and make sure you're in the correct environment by checking the text within the parentheses here. If it's not displaying the name of the desired environment, then you need to activate it with Conda, activate, speech, environment. Good. Now, to install Librosa, type pip, install Librosa, and hit enter. Okay. What comes next is the Speech Recognition Library, an essential tool for converting spoken language into written text. This library supports multiple speech engines and APIs, including Google Web Speech API, Microsoft Bing Voice Recognition, and others, making it flexible for various purposes. It allows you to capture audio from microphones, process audio files, and convert speech to text accurately. To install it, type pip install speech recognition. Please ensure you type it correctly. Don't separate the two words with a blank space. And don't forget that Python is case sensitive. After the installation is complete, we'll proceed with WER, a valuable library for evaluating the performance of speech recognition systems. WER provides tools to measure the word error rate and character error rate between a reference text and a predicted text. These metrics are essential for understanding how accurately a speech recognition system works, and we'll discuss them in more detail later. Just like before, execute pip install WER and wait for the process to finish. Good. We'll also need matplotlib, a comprehensive library for creating visualizations in Python. Type pip install matplotlib and hit enter. We'll also need the Google Text-to-Speech library, which allows you to convert text into spoken language. You'll see how fun that is later. For now, let's include this library as well. Okay, let's now install the renowned Whisper AI from OpenAI. Whisper AI is a powerful machine learning package designed for high-quality speech recognition. It enables accurate transcription and understanding of spoken language. This is probably the most challenging installation process of all. Don't worry, we'll explain it clearly and step by step. To make Whisper function properly on our local system, we first need to install PyTorch, a robust library for machine learning. So go to the PyTorch homepage, click Get Started, and scroll down to the Start Locally section to configure the settings. We aim to install the current stable version, so select that option. Since I'm using Windows, I'll choose that as my operating system. I'll also select pip as the package type and Python as the preferred programming language. Next, choose the computing platform. If you have a high-end graphics card like NVIDIA or AMD, select a recent version of CUDA. Otherwise, select the option on the right if you use the CPU instead of the GPU. Once you've made all the selections, copy the provided code and paste it into your command prompt or terminal if you're on a Mac. Press Enter and wait for the installation to complete. Okay. Next, download Chocolatey, a Windows package manager. If you're on a Mac, I recommend downloading Homebrew and following identical steps. So I'll go to Chocolatey's homepage and click Install in the top right corner. Choose Individual from the relevant section and copy the text in the field below. Next, find Windows PowerShell from the search menu and run it as an administrator. Do that in Terminal if you're on a Mac. Then press Ctrl+V to paste and execute the copy text. Hang in there, everyone, we're almost finished. Now that we have Chocolatey, we'll use its package manager to install FFmpeg, a powerful and versatile open-source software suite for handling multimedia data. WER requires FFmpeg to handle various audio file formats such as WAV or MP3. Type choco install FFmpeg. Hit Enter and choose Yes. Great. We've reached the final step, installing WER itself. Open the command prompt and type pip install -u OpenAI-WER. This command will install WER or update it if you already have a version installed. Once the installation is complete, you're all set. We now have WER ready for speech to text. You can now type pip show OpenAI-WER to ensure you have the package installed correctly. Excellent, we're good to go. We now have the necessary libraries for our speech-to-text exercise. It's time to start using them. Before we jump into the fun part, let's briefly talk about the packages we'll use. Launch Anaconda and ensure the correct environment is selected. Then check if the Jupyter Notebook application is installed. If not, press Install and wait for the process to finish. Then hit Launch and wait for it to load. Okay, welcome to Jupyter Notebook. If you're unfamiliar with its interface and want to learn more about it, our colleague Martin created a dedicated course on Jupyter. Feel free to check it out. Jupyter Notebook is a web-based tool that allows you to write and run code in an interactive environment. It supports Python and lets you combine code, text, and visualizations in a single document. This makes it great for data analysis, research, and educational purposes. You can execute code in individual cells and see the results immediately, which helps you explore data and test ideas quickly. All right, let's import the relevant packages in the first cell from our notebook. Start with NumPy, a third-party package for working with multi-dimensional arrays. Import it as NP, which is the standard abbreviation convention. We'll also benefit from the matplotlib pyplot collection to create essential visualizations. Next, we'll need Librosa, a library for audio and music analysis and manipulation. We'll also use Librosa.display for visualizing audio data. Soundfile is used to read and write sound files. It supports various file formats and provides an easy interface for manipulating audio data. Next, we'll need SpeechRecognition, the library for converting spoken language into written text. WER comes next as a library for measuring word error rate and character error rate in speech recognition tasks. These are key evaluation metrics. We'll also use IPython, which provides a rich toolkit to help us make the most out of using Python interactively. It includes the IPython.display module for displaying media files like audio. Of course, we'll use the WER library extensively for advanced speech recognition and processing. We'll also need CSV for reading and writing CSV files, OS for interacting with the operating system, Tempfile for creating temporary files, and WAV for reading and writing WAV files. Finally, add the GTTS class from the Google Text-to-Speech library, which converts text into spoken language. Let's execute this cell to import the relevant packages for speech recognition. Now, let's roll up our sleeves and get to work. See you soon. Hey everyone! Have you ever wondered about the different types of audio files like MP3 and WAV, and what distinguishes them? Truth is that all audio files represent the way the file is stored after its analog to digital conversion. The key difference between these formats is how they handle this data transformation. Some formats prioritize sound quality, aiming to preserve every detail, while others focus on file size, compressing the data to save space but sacrificing some quality in the process. The quality and characteristics of your audio files can significantly affect transcription accuracy. Moreover, some speech-to-text models even require specific audio formats, so you won't be able to transcribe the file unless it's converted to the required type. In this lesson, we'll break down the critical distinctions between standard audio formats and explore why you might choose one over the other when building or using a speech recognition tool. Let's dive in. First, we have the WAV, or Waveform Audio File Format. Like all audio formats, WAV is a digital representation of the analog signal. It's an uncompressed type, meaning it retains almost all of the audio details from the analog version with minimal data loss. WAV files support high sample rates up to 192 kHz and bit depths up to 32-bit, which capture detailed sound waves. Recall that the sample rate refers to how often the audio signal is measured per second, and the bit depth refers to how much detail is captured in each sample, with higher bit depths offering more precision. So 192 kHz is the same as 192,000 Hz, meaning the signal was sampled 192,000 times per second. A 32-bit bit depth means that each sample in the audio can store 2 to the power of 32 different sound levels, which equals about 4.3 billion possible values. This incredibly high resolution allows a tremendous dynamic range, meaning it can capture quiet and loud sounds with extreme precision. This is excellent quality. WAV files, however, are uncompressed and typically large, making it more challenging to store or transfer substantial audio data, particularly with longer recordings or when storage space is limited. Despite this, they offer the best quality input for speech-to-text systems by preserving every nuance of the original audio, making them perfect for applications that require precise transcription. Next comes FLAC, or Free Lossless Audio Codec. FLAC offers lossless compression, which reduces the file size without losing audio quality. It's particularly useful when working with longer recordings because it maintains almost the same high fidelity as WAV files but is more manageable in size. This format can handle sample rates up to about 650 kHz and bit depths up to 32 bits, making it an excellent choice for speech recognition applications where quality and file size are important considerations. But while FLAC provides lossless compression, which preserves audio quality in a smaller file, WAV files are often preferred in professional settings. They are uncompressed and more universally supported by many audio and transcription systems. WAV files ensure maximum compatibility and avoid any possible issues with compression or decoding, making them the gold standard for speech-to-text applications. All right. I suppose you've heard of MP3, which derives from MPEG Audio Layer 3, a standard for compressing audio files. MP3 is one of the most common audio formats. This format reduces file size by discarding some audio data that can affect the quality. Nevertheless, MP3 files can still deliver decent audio at higher bit rates. MP3 is suitable for general speech-to-text applications where file size and storage are concerns, and extreme accuracy is not critical. It's a practical choice for everyday use cases like transcribing podcasts or casual recordings, where a balance between quality and file size is acceptable. All right, what's next? AAC, or Advanced Audio Coding, is another format that uses lossy compression like MP3 but offers better sound quality at similar bit rates. AAC is widely used in streaming and digital broadcasting. Its efficient compression makes the format a good option for speech recognition applications, especially in environments with limited storage space such as mobile or online platforms. It's essential, however, to consider the trade-off between compression and quality, particularly in more demanding applications. Lastly, we'll introduce M4A, or MPEG-4 audio, known for its efficiency and quality. This format is commonly used in mobile and streaming applications, making it a practical choice for cloud-based transcription services or mobile device processing. M4A supports both lossy and lossless compression, providing flexibility to choose the optimal format for your needs. Great! In summary, when choosing an audio format for speech recognition, you need to consider the specific requirements of your application or the speech-to-text tool. WAV and FLAC are best for high-quality applications requiring high fidelity, while MP3 and AAC offer more flexibility with smaller file sizes, suitable for everyday use cases. M4A provides a balanced approach, especially for mobile and streaming contexts. What is crucial is to always check on what your model needs. Some speech-to-text tools might expect a WAV file with a specific sample rate, while others might even work with highly compressed MP3s. And if your audio isn't in the required format, you could convert it using various tools and methods. For example, you can use free software like Audacity or FFmpeg to change the format and adjust the sample rate, ensuring compatibility with your chosen speech recognition system. You can accomplish this directly in Python using popular audio processing libraries like Librosa, which we'll explore later in the course. All clear, right? Let's wrap up our discussion on audio files. Feel free to play your favorite song and check out its format on your device. Now you know exactly what it means. See you in the next lesson. Thanks for watching. Hi. In this lesson, you'll learn to import, visualize, and play an audio file directly in Jupyter Notebook. Before you start, please download the Speech01 audio file from the resource section and save it in the same folder as the notebook you'll be working on. Otherwise, you must specify the file's location so Jupyter can recognize it. Okay, we'll use the load function from the Librosa package to import the audio file into the notebook. The load function reads an audio file and returns two values. The first is a NumPy array representing the audio signal's amplitude over time. In other words, the waveform of the sound file. We'll store this in a variable called audio signal. The second value is an integer corresponding to the sample rate measured in hertz, which indicates how many audio samples are captured per second. We'll store this in a variable called sample rate. Separate the two variables by a comma, then type an equal sign followed by librosa.load. This way, we're instructing the code to assign the values returned by the librosa.load function to those two variables. In the parentheses, pass two arguments: the audio file name speech01 and SR equals none, which will guarantee the audio is loaded at its original sample rate. Here, we could specify a different sample rate and resample the audio file. But why would we need to do that? We might need to resample the audio when working with machine learning models or audio processing algorithms that require a specific sample rate. For example, some models may perform better with a sample rate of 22,050 Hz. Or we may need to match the sample rate of other audio files in our project for consistency. For now, we won't change this parameter. Instead, let's execute this cell and display the sample rate variable in another one. The output shows 44,100 Hz. This means the audio file is sampled 44,100 times per second, the standard sample rate for high-quality audio such as CDs. Great. A good approach to investigating this audio file would be to visualize it and, of course, hear it. But how do we visualize audio? Naturally, by showing its waveform, a graph of the audio signal's amplitude over time. Well, let's do that using Matplotlib's PyPlots collection. In a new cell, type plt.figure. I'll use 12 by 4 inches for the figure size, but feel free to improvise with different dimensions. Good. In the next line, we'll use Librosa to plot the waveform of the audio signal. Type librosa.display.waveshow. The function's first argument will be the name of the variable storing the audio data, and the second one will be the sample rate variable. This way, Librosa will plot the amplitude of the audio signal over time. We'll add a title and labels to the plot in the following lines. Let's name the graph Waveform. Label the x-axis as time measured in seconds and the y-axis as amplitude. Finally, we'll use the show function to display the plot. Well, that's the code for displaying the file, but we also said we wanted to hear it, right? To achieve this, type audio with an uppercase A to use the relevant function from the IPython display library. Place the name of the file in the parentheses. Okay, I think we're good to go. Execute. Excellent. We see both the visual representation of the signal and a player allowing us to start the recording. Let's press play and listen to it. My name is Ivan, and I am excited to have you as part of our learning community. Before we get started, I'd like to tell you a little bit about myself. I'm a sound engineer turned data scientist, curious about machine learning and artificial intelligence. My professional background is primarily in media production with a focus on audio, IT, and communications. Well, that's a noisy file, isn't it? Don't worry, this is on purpose. But let's concentrate on the visuals for now. The y-axis indicates whether the sound is loud or soft, with higher values corresponding to louder sounds and values closer to 0 representing quieter moments. These values relate to how much air molecules deflect from their equilibrium. The positive and negative values represent the back and forth vibrations of air particles as the sound wave travels. The positive values show when the wave pushes the particles forward, and the negative values show when the wave pulls them back. In digital audio, however, we don't measure actual air particle vibrations. Instead, we represent the amplitude of the sound wave as numerical values, typically normalized between -1 and 1. So when we see values like -0.75 to 0.75, the loudest parts of the audio reach 75% of the maximum possible amplitude in positive and negative directions. This maximum amplitude is the highest level the audio can reach without clipping. Okay, but what's clipping? Clipping occurs when the signal's amplitude exceeds a certain limit and causes distortion, an unwanted change in the audio signal that makes it sound harsh or unclear. You've probably heard such a distorted sound like when someone talks too close to a microphone. Yeah, I know, it's not nice. The 75% value guarantees that the audio levels remain consistent and prevents distortion, keeping the sound clear and pleasant to listen to. The closer the amplitude is to 0, the less intense the sound. The further the amplitude is from 0, the louder the sound is at that moment. So a high absolute amplitude value, positive or negative, indicates a louder sound. Okay. The time axis indicates the duration of the audio in seconds. Each number represents a point in time. 0 is the start of the audio, 5 is 5 seconds in, 10 is 10 seconds in, and so on up to 23 seconds. The graphs show that the signal is quieter at the beginning and becomes louder 2 to 3 seconds later. Well, this is where the speech starts. So the graph makes sense, right? The symmetrical shape of the waveform indicates the balanced variations in air pressure, accurately representing the audio signal's changes over the 23-second duration. The visualization helps us understand the structure and dynamics of the audio, making it easier to identify key events like the start of the speech. By analyzing the waveform, we can gain insights into the intensity and timing of the sounds within the recording. All right, let's take a break and process this audio knowledge. Hello again. It's time to get familiar with some of the widely used speech-to-text methodologies. In this lesson, we'll talk about the famous speech recognition library. Well, it's not exactly world famous unless you're a speech and sound tech nerd, but guess what? Now you are, so wear it with pride. The speech recognition library is a powerful and easy-to-use Python tool for converting spoken language into written text. It supports various speech recognition engines and APIs, including Google Web Speech API, Microsoft Bing Voice Recognition, and more. With its simple interface, speech recognition makes it accessible for users to integrate speech-to-text functionality into their projects, whether for voice command applications, transcription services, or interactive voice-driven programs. So, what are we waiting for? Let's learn how to use it. First, we must utilize the Recognizer class, a vital component of the speech recognition library. This class provides various methods and functions for recognizing speech from different sources, such as a microphone or an audio file, and supports multiple speech-to-text APIs. To initialize the recognizer, create an instance of the said class using the speech recognition library. Let's store it in a new variable, naming it intuitively to reflect its purpose. This way, we can easily reference the recognizer throughout our code. Great! We now have our first speech-to-text tool ready to use. So, let's do it. Before transcribing our audio file, I'll store its path in a variable called filePath for later convenience. This makes the code more flexible and easier to maintain. In our case, we don't need to specify the file's absolute path, only its name, because we placed it in the same directory as the notebook. Storing the file path in a variable is always good practice because, first, it keeps the code clean and organized. Second, it makes it easier to update the path if the file location changes. And third, it improves code readability and maintainability. Good to know. Let's now use the recognizer to create a function that takes a file path, processes the audio, and returns the transcribed text. In a new cell, I'll start by typing def to define our function and intuitively name it transcribe_audio. I'll set file path as a required parameter. This way, the function expects a path to the audio file. All right. Now, we need to open the audio file in the function's body. As you can imagine, opening a file uses some of the computer's resources. Therefore, forgetting to close the file upon use can lead to severe issues such as memory leaks. To avoid this, best practice recommends using Python's with statement. The with statement automatically closes the file after use, preventing resource issues without us needing to remember to close it. This is another critical best practice to remember when handling audio or other media files. Great! After with, I'll use the audio file class from the speech recognition library. Audio file will take the path to the audio file and prepare it for further processing. I'll end this line by typing as source, assigning the opened audio file to the variable source. Good. In the next line, I'll create a variable called audio data. Following an equal sign, I'll reference the instance of the recognizer class and use it to invoke a method called record. It captures audio data from a specified source and passes it as an argument. The record method listens to the audio from the source and takes the sound data available in the audio file. Then it converts the audio into a format that can be processed by the speech recognition library, storing a numerical representation of the waveform. This is what we'll keep in the audio data variable. In the next line, I'll send the captured data from the audio data variable to the Google Speech Recognition API using the Recognize Google method. The API is expected to process the audio data and return the transcribed text in a variable called text. Great. Next, print the text to see if it all will work as expected. We'll also return the transcribed text from the transcribe audio function, allowing us to use it elsewhere in the code. Finally, I'll add a line for calling the function with the relevant file path using the appropriate variable. Let's execute this cell and wait for the output to appear. There it is, our first speech-to-text transcription. At first sight, it looks pretty good, doesn't it? Although this is not the correct way of writing my name, the other part of the text seems more or less accurate. Let's break down what happens after we've executed our code. Once recorded and stored under audio data, the sound data represents a digital signal capturing the amplitude variations of the sound wave over time. When we pass this audio data to the Google Web Speech API via the Recognize Google method, several vital steps happen on their servers. The API first transforms the waveform into a spectrogram, a visual representation of the sound frequency's components over time. You might recall from earlier lessons that the short-time Fourier transform is often used to break the time domain signal or waveform into a frequency domain representation or spectrogram. Next, deep neural networks such as CNNs are employed as part of the acoustic modeling mechanism to recognize spectrogram patterns corresponding to specific phonemes. Once the phonemes are recognized, the system uses language modeling to determine how they come together to form meaningful words and sentences. Deep neural networks such as RNNs and transformers predict words and phrases based on the recognized phonemes and context. Okay, after Google servers process the audio, they convert the spoken words into text and send it back to our application. The Recognize Google method receives and assigns it to the variable with the appropriate name. Let's summarize. The speech recognition library is an easy-to-use interface that sends audio data to different speech recognition services, like Google's Web Speech API. It doesn't contain or run speech recognition models. It simply helps you interact with external services like Google's API. The API is where the heavy lifting happens. Once the audio is sent through the Recognize Google function, Google servers process the data using their acoustic and language models. These models convert the audio into text using machine learning algorithms such as deep neural networks or transformers. So it's all clear. Let's now look at the transcription we've just made. I can definitely notice a few shortcomings. Firstly, there are no punctuation marks within the text. Secondly, the words term and in seem out of context and may not be correct. This indicates that the transcription is probably not perfect. But to properly evaluate the result, we need to assess the transcription's accuracy and identify any errors or misinterpretations using proper tools. We'll do this with the help of two metrics, word error rates and character error rate. We'll talk more about these in the next lesson. See you there. Word error rate, or WER, and character error rate, or CER, are key metrics used to evaluate the accuracy of speech recognition systems. Let's explore what they represent. WER evaluates the accuracy by measuring the percentage of incorrectly recognized words in a transcription. It considers substitutions, insertions, and deletions of words. A substitution is when a word in the spoken input is incorrectly replaced with another word in the transcription. For example, if cat is spoken and the system transcribes it as bat, this counts as a substitution error. Insertion means adding an extra word not present in the original spoken input. For example, if cat is spoken and the system transcribes it as the cat, the word the is an insertion error. Deletion represents a situation where the system fails to include a word that was present in the spoken input. For example, if cat is spoken and the system transcribes nothing, it's a deletion error. Okay. WER is calculated as the sum of all these errors divided by the total number of words in the reference transcript. The result is then multiplied by 100 to get a percentage. Therefore, a lower WER indicates higher accuracy, meaning fewer errors in the transcription process. Pretty straightforward, right? CER, on the other hand, focuses on individual characters rather than entire words. Like WER, CER considers substitutions, incorrect characters, insertions, extra characters, and deletions, missing characters. It calculates the total number of these character errors divided by the number of characters in the reference text, then multiplies by 100 to give a percentage. A lower CER means the system is more accurate in recognizing the correct characters. Good. WER and CER offer valuable insights into the effectiveness and reliability of speech-to-text models, highlighting areas for improvement. They're primarily used during the training phase of a model to measure and refine its accuracy. Calculating WER and CER allows us to identify specific areas where the model misinterprets speech, enabling us to adjust and improve the system. These metrics, however, are also valuable for assessing the performance of a fully developed speech recognition model, providing ongoing quality assurance as the system encounters new data. In the following lesson, we'll apply WER and CER to evaluate the accuracy of the transcript we just created, showing how these metrics help determine the effectiveness of a speech-to-text system. See you then. Let's return to our Jupyter exercise and use these two essential metrics to evaluate the quality of our transcript. To evaluate a transcript using WER and CER, we first need a reference transcript, often called the ground truth. The ground truth is the accurate, manually verified transcription of the audio content, which serves as the standard for comparison. In other words, the ground truth is the accurate text against which the transcription is assessed. It provides the benchmark for measuring the accuracy of the speech recognition system. WER and CER are calculated by comparing the errors in the obtained transcription against the ground truth. I'll assign the original text from the audio file to a new variable, which I'll name appropriately. You can find this text in the attached TXT file from the resource section of this lesson. I'll use triple quotation marks, which allow me to include the entire text block, even if it spans multiple lines or contains special characters. Great. Let's implement the essential speech recognition evaluation metrics in our code. In Python, the GWER library provides functions for calculating WER and CER. Using these functions is straightforward. Type WER and as arguments, place the ground truth and the variable in which we stored the transcribed text. Pass the result in a variable called calculated WER. Let's do the same for CER and then print both results. Additionally, I'll format the output to show 4 digits after the decimal point. Let's execute and see what we'll obtain. The word error rate is 0.3390, meaning that about 40% of the words in the transcription are incorrect compared to the ground truth. That sounds like a lot. Let's break down why that is. The transcribed text contains several substitution errors with misrecognized words. For example, Ivan, which is my name, was written as YVONNE. I suppose that's fine, though I'm not thrilled about it. Let's see what else we can find. We observe that artificial intelligence was capitalized in the ground truth, but not in the transcript. These errors fall into the substitution category. The same goes for other transcript parts with no uppercase letters. Yes, the meaning remains identical even with these errors, but the specific words used are different, regardless of how slight those differences are. Furthermore, as we mentioned previously, the word term is used here instead of the correct turned. The same goes for machine learning in artificial intelligence, where the word in is wrongly used instead of the correct one, and. These substitutions alter the sentence's meaning or result in an interpretation that makes no sense. Overall, such errors significantly impact the WER because minor changes can quickly accumulate, particularly in shorter text where every word dramatically affects the total error rate. This emphasizes the importance of using accurate and context-appropriate speech-to-text algorithms. For example, models that incorporate punctuation are likely to handle capitalization better. Regarding punctuation, absent in the transcript, let's focus on another crucial metric, the character error rate. We see that CER is 0.0884, meaning that approximately 9% of the characters in the transcription are incorrect compared to the ground truth. CER considers each character individually, including punctuation, capitalization, and every distinct character in the text. And as we saw, there is no punctuation in the obtained transcript. Initially, you might think that, as opposed to WER, the CER result looks low, only 9%. But keep in mind that the ground truth has 471 characters, excluding spaces. This means that approximately 42 characters are wrong in the transcription, which is not a low number. CER is sensitive to all differences, including punctuation and capitalization, which are crucial for accurate representation and meaning in text. The key takeaway here is that our goal is to achieve lower WER and CER values. To do this, we can either process the audio file to improve the transcription tool's performance, or try a different tool to see if it yields better results. As you may recall, the audio file contains significant noise. So, what do you think? Would the model work better if we reduce the noise a bit? We'll try that in the upcoming lessons. To do that properly, we'll learn to visualize spectrograms, an essential tool for identifying a sound file's frequencies, patterns, and dominant noises. See you soon.